Greetings everyone. I am honored to present my research work in the second International Multi-Topic Conference IMCES. My paper ID is 161 and the title is Implementation and Performance Analysis of Bidirectional Free Space Optical Channel in Hybrid TDM-WDM Gigabit Passive Optical Network. Let's take you to the presentation skeleton. The main sections are introduction, then system architecture, experimental results, conclusion, acknowledgement, and references. The growth of sophisticated and intelligent devices, which brings the need of virtually always stay connected with anything and everything we can think of, is creating a demand of high data rates which could support the triple play. So there is a massive deployment of fiber to the home service to provide more and more users high speed internet and all other facilities of triple play that includes HDTV and Wi-Fi and voice communication and data usage and so on. So the passive optical network architecture is adopted across the globe in order to provide higher bandwidth support, and this is the general layout of passive optical network. More specifically, the gigabit PON is shown in this diagram, or GPON, provide a powerful multi-point, this is your point, to multi-point solution to satisfy the increasing capacity demand in the access part of the communication infrastructure. The gigabit PON is fast, efficient, reliable, and it is future-proof. All different requirements of the subscribers or the users, like HDTV, high-speed data, Wi-Fi, voice, all have the same solution, everything included solution, that is GPON. Now, the hybrid GPON is basically a hybrid passive optical network where WDM and TDM GPON are integrated into a single passive optical network. For downstream communication, we use WDM. For upstream, WDM plus TDM. That is why it is called hybrid. At the user end, the deployment of free space optical channel instead of optical fiber is the main focus of this work. FSO can be considered as an alternative to the optical fiber cable or RF or microwave system, especially when the physical connections are impractical due to several considerations, and it has become the ideal choice for the access technology. PLA in 2011 has worked on TDM WDM GPON utilizing 2.5 gigabit per second rate for downstream and 1.24 gigabit per second rate for upstream. The author has taken 5 areas as shown in this picture for performing the simulation, and the system is completely optical fiber based. The main bidirectional optical fiber connecting the optical line terminal to the optical distribution network is of 5 kilometers in length. At the access network side, the length of these bidirectional optical fiber in each area is different depending upon the requirements of that area. So in this work, we are implementing FSO channel at the optical distribution network or optical network unit side, and the backbone fiber cable has a length of 50 kilometer, and there are two different areas which are simulated, namely hospital block and building block. Each block has a free space optical channel for upstream and downstream, and the FSO channel length is one of the major issue which can impact the performance of the system. So the objective of this work is to take 5 different ranges from 50 to 250 meters and analyze the system performance. Considering the tropical environments like we have in Pakistan or India, this system is going to provide performance in terms of Q factor and bit error rate along with eye diagrams. And the bit error rate of the order of 10 raised to the power minus 16 and 10 raised to the power minus 12 has been recorded in this work simulation. Okay, so the next slide is system architecture. This is a complete system architecture of this work. You can see 3 sections. This part is known as optical line terminal, and this is the backbone channel, and this is the access or the last mile network. And you can see we have taken 2 areas. One is hospital block, another is building block. And in this optical line terminal section there are basically 2 parts, because this is a bidirectional system, means you can have downstream as well as upstream communication. So this part is for downstream, and this is the bidirectional circulator, and because of this bidirectional circulator we have connected here the upstream connectivity. And okay, so for explaining the architecture, let me first take you from downstream connectivity. In the downstream we have a WDM transmitter having a frequency of 1450 nanometer, and we are taking only 2 for the sake of simplicity. We are taking only 2 areas. So we have 2 wavelengths, 1450 nanometer and 1470 nanometer at the frequency spacing of 20 nanometers. So these 2 wavelengths are multiplexed using a WDM multiplexer, and then to have a good quality signal transmission, an optical amplifier with a gain of 15 dB is connected here. Then the signal is going to pass through a bidirectional circulator, and bidirectional circulator is very important because we are performing 2-way communication. So when the downstream signal passes from this circulator, it is going to cross the backbone channel, that is your main optical fiber. This is a bidirectional optical fiber having a length of 50 kilometers. Once the signal passes from this backbone channel, it is going to reach to the access network, and in the splitter, this splitter is going to split the wavelengths, and the signal are going to be passed to hospital and the building blocks. Inside this block, this hospital block, we have you can see here 2 free space optical channels, one for downstream, another is for upstream. And this downstream free space optical channel is connected with the optical network unit of the hospital block, and the output from the ONU is connected with the bit error rate analyzers for observing the system performance. Inside this ONU we have a receiver circuitry, that is photodiode, and that is connected with the low pass special filter. So this is all the connections requirements for the downstream communication. Similarly, the same connections are being done for the building block, and the only difference is that it is a little bit having 2 buildings, so it is going to have 2 different connections and so on. For sake of simplicity, I have only hospital block is explained here or presented here. So now let's come to the architecture of upstream communication. For the upstream communication, now this ONU will become the transmitter and this OLT will become the receiver. So you can see that here we have an optical transmitter with a frequency of 1270 nanometers. For every block we will have different wavelength, but if inside the block we have multiple buildings or blocks, then we will need to use time division multiplexing that is performed in the building block. As in the hospital block, there is no such block, so the optical transmitter is directly connected to the ONU, and to the outside of the ONU we have the upstream FSO channel. Again, it will vary its length from 50 to 250 meters. That is going to be connected to the backbone channel using bidirectional optical fiber having length 50 kilometer. The signal is going to reach the circulator, and this part is the receiver side in the OLT, that is for the upstream. And for that we have the photodetector, low pass Bessel filter, we have buffer selector, and that is connected with the bit error rate analyzer. Okay, so the experimental results. Now when simulating this design, you can see here in this figure we got downstream results for hospital block. For the free space optical channel 50 meters, and this one is for 100 meters. So you can see that with the 50 meter the eye diagram is very clear and very wide, eye opening, and at the 100 meters range the signal has started to degrade, but still we are having a good performance, because here the bit error rate is of the order of 10 to the power minus 10. But as soon as we go further in the length, like for 150 meters and so on, the signal completely deteriorates and there is no transmission. Similar results are received at the big building blocks. This diagram is for 50 meters and this one is for 100 meters. In this diagram, Q factor for 5 iteration is shown. For the 50 meters we have a very high quality factor. For 100 meters it's also very acceptable. At 100 meters the quality factor is 6.22, but as soon as it goes to 150 meters the quality factor reduces to 2.14, and for the other two distances it completely becomes 0. So till 100 meters one can say that FSO channel or WDM TDM hybrid system is applicable. This graph also shows the performance of the system for downstream communication, where we have plotted a minimum log of bit error rate versus total power of the users, and you can see here in this diagram that as soon as the distance in the power increases, the graph is decreasing. So at 50 meters the bit error rate produces peak performance, as at this point the bit error rate is achieved up to the order of 10 to the power minus 176, and at 100 meters the bit error rate value is 4.91 into 10 to the power minus 16, and after that bit error rate degrades significantly. And in this diagram the upstream communication is shown, the performance is shown here. This eye diagram is for 50 meters and this one is for 150 meters, and you can see clearly that at 150 meters the eye opening has reduced significantly, and the bit error rate is not in the range of 10 raised to power minus 9 or less. So the conclusion is the bidirectional free space optical communication channel are providing good quality data transmission in hybrid GPON system at the range of 50 to 100 meters. The bit error rate of the order of 10 to the power 16, minus 16 and minus 12 at a distance of 100 meters for both upstream and downstream communication is achieved. But if the range is greater than 100 meters, the system performance deteriorates significantly. Therefore, careful considerations must be taken while installing free space optical channel for distances greater than 100 meters in TDM, WDM, GPON. We are thankful for the support of Memon University of Engineering and Technology, Pakistan. These are the references.